Good afternoon, one and all. You're not late. I've only just hit the record button, so you're perfectly on time. So welcome back. First week back after term break. We will be kicking off with IPv6 addressing today. Now, hopefully you remember some of the IPv4 stuff that we did last term. You had the whole 2 weeks of break to read the chapter and make sure you're up to speed. And of course you did that. I know you're all good students and do what I ask you to do over the term break. Alright, so in this chapter we'll look at why we needed IPv6 to come into existence, how addressing is represented. We'll look at the types of addresses that occur under v6. There's a little bit of difference between v4 and v6. And we'll look at some of the configuration for IPv6. It's not that much different to v4 in format. Just a little bit more typing to get the extra characters in. Not too bad. And we'll look at the Unicast addresses and how they can be dynamically assigned for hosts, and how LinkLocal addresses occur, how you can identify the various IPv6 addresses for whether they're multicast or belonging to a subnet, and how to recognize that. So what were the issues in IPv4 that caused IPv6 to come into play? Basically, we ran out of addressing. In a nutshell, as simple as that. Doesn't have to get much more complicated than that. We did some patching in IPv4 that extended the life of v4. So we introduced CIDR notation, which is classless interdomain routing, which made it so that we didn't have to have every chunk of the network exactly the same size. So we could have variable length subnetting. And we also introduced network address translation and port address translation. Everybody just calls it NAT, but it's actually two different protocols. It's NAT and PAT. So one just translates IP address to IP address, and PAT translates multiple IP addresses and applications to one IP address. Okay, so it's actually NAT-PAT that we're all used to seeing on our home routers and that. That's where we can get many to one address translations occurring. So these additions to IPv4 only extended the lifespan of v4 whilst IPv6 was being finalized. So we have increased the available addressing pool considerably by going from a 32-bit address to a 128-bit address space. And this has allowed us to really embrace the Internet of Things and other technology changes and the way we work into the future with everything having an IP address and being connected to a network in one form or another. So for the time being, as we transition across to IPv6, both IPv4 and v6 will coexist for a number of years still, and there's a number of techniques that are being used during this transition period. One of them is dual stacking, where we run both v4 and v6 addressing spaces on the interfaces at the same time. Tunneling allows us to connect pockets of addressing to each other using a tunnel, pretty much like a VPN. So we just encapsulate the IPv6 packets with a new header so that IPv6 doesn't see the IPv4 network, for example. And we can do translations between network address translations between IPv6 and IPv4. This is NAT64. That's not the preferred method, obviously, because of you can have so many more addresses in IPv6 than you have in v4. So that's the least preferred method during the transition between them. So IPv6, how's it represented? So we have a number of addresses represented in hexadecimal. Okay, so 128 bits, but we're writing it in hexadecimal numbers. Now, cast your mind back when we did all that decimal, binary, hexadecimal conversions. This is the reason why. So basically what we're doing is we have a little hextet which is being used to represent 16 bits or the 4 hexadecimal values. Now each set is separated by a colon, and we can have a whole set of rules governing how we can shorten the notation of this, which we'll go through in a second. So the first rule of hexadecimal is that we can always omit a leading 0. Now, the reason we can do this is we know that between each set of columns there should be 4 hexadecimal digits. So by omitting the leading 0, we're not changing the value between the 2 columns, because leading zeros do not change the overall value of the bits in that segment. So we know exactly how many zeros to put back when we need to use the address. So we can use this as many times as we like within the v6 number, because we know exactly that there's 4 digits, and we just, in this example here where there's just a single 0, we know there's another 3 zeros to go in front. You never delete a trailing 0. It's only ever the leading zeros, because leading zeros do not have an impact on the value trailing zeros do. We can replace a series of zeros by using a double colon. We can only do this once within a sequence, and basically when you have a large number of zeros grouped together, you can represent those as just a single double colon, because we can always recalculate out back to the full number by putting the zeros back in. This is why we can only use it once, because it's a variable length, and it can go across the little hextet boundaries. So we don't know how many zeros can be in there if we use it twice. All right, that's why using it twice wouldn't work, because we wouldn't know how many zeros to put back. But by using it only in one position, we can calculate how many zeros to put back into the number. All right, the only change as far as our 3 categories of transmission is the last one, Anycast. Anycast effectively is replacing broadcast in IPv4. So Unicast works exactly the same, one-to-one, multicast, one-to-many, and Anycast is assigning it to a group of devices, multiple devices. It's kind of like a broadcast, but not all. It's a little funny, but you'll get used to it. So prefix length is by default 64/64, and the reason this is because we've split the 128 bits into 2 portions. So the way it works is the first half is always going to be a network. Okay, that's global. That's network prefixes on the first 64 bits. The last 64 bits is dedicated to identifying your individual interfacer. So if you cast your mind back, there's a thing called a network card with a MAC address that is also in hexadecimal, but that's only 48 bits in length. So we'll touch base on how we can change that into 64 bits in a few slides, but it's available there and we can do it with some funky business. So standard format is first half network or prefix, last half interface ID, so or host if you like. Can you change that? Yes, you can, by changing the /64 to something else. Of course you can, but it's not recommended because we can use stateless address auto configuration to generate this interface ID quickly and easily, and it also makes subnetting very simple. So basically we have a global unicast address and a LinkLocal address. So a global unicast address is the one that is assigned to the interface and is routable via the internet and every other network. Okay, so this is the one we logically assign to the interface, just like we would do with IPv4. The other one is the LinkLocal address, which is generated automatically by the interface and is not routable. It is confined to that link. So if you cast your mind back the way Ethernet works, it's like working on a shared cable. So the LinkLocal addresses are like addresses that would occur on that shared cable. Okay, so just on that network segment. Okay, so unique local addresses range there from FC00 to FDFF/7s, and they have something like the old private numbers, which yeah, don't worry about it, Cooper. Once we get in and do some configurations and stuff like that, it will become a lot clearer. There are a number of packet tracer activities to help cement all of this into place in this chapter. So it'll all become clearer after you start playing with it a bit. So just like we have in IPv4 with the 10.0.0.0 network, the 172.16 to 172.31 networks, and the 192.168 networks that anybody can use in their private networks. The FC00 to FDFF are basically like the same. So yeah. So I'm glad you're finding them useful, Jacob. Yeah. As we can't get in to do practical labs at the moment, yeah, packet trace is our best friend for doing it, and it's not a bad package for learning. We can do quite a bit with packet tracer, and as long as you use the command line interface option within the configurations and not the shortcuts, you'll learn exactly how to configure the devices, like if you're using live devices. So yeah. Trust me, it all fades away if you're not using it, Cooper. So yeah. All right, so that's our unique locals, and global unicast addresses are generally routable and unique, and basically they start with the 001 prefix on the front. Okay, so basically they all start with 2000 sort of thing, which is a bit strange to but yeah, so 2000 to 3 triple F, which is an eighth of the total of available IPv6 addresses at the moment. So these will change as they are adopted more. Cheat sheets are good. Yeah, I'll have to find my V6 exercise booklet, but I've got a booklet that I was going to post up for you guys to do practice with IPv4 addressing. It's just a PDF booklet that has a whole series of addresses for you to calculate, so you get used to calculating addresses and assigning addresses and things like that. Okay, so there used to be an IPv4 and a V6 booklet. I've misplaced my V6 one, so I'll have to find it. But I'll upload it again for you guys. Okay, IPv6 GUA structure, global routing prefix, then subnet ID, and then interface ID. So pretty much like we would do with V4, we start with the original network, break it up into subnets, and then have a host ID at the end. So the structure is the same, just the way it's applied is differently. So basically the first one in your global routing prefix will be given to you by basically your ISP, and this prefix length will vary depending on where you are in relation to your ISP and how many addresses you need, and they will give you a subnet ID length. So if you're a big enterprise, they might give you a couple of digits or 3 or 4 digits, depending on your requirements for subnet ID. Okay, and basically the global routing prefix and subnet ID are still normally within that first 64-bit prefix length, and that leaves you the 64-bit interface ID as normal. Now, as we said, you can change your prefix length and bring it into the interface ID. Can do that, but it means you've got to do a little bit more manual addressing throughout your networks. LinkLocal addresses, as I said earlier, are only on that cable, so they will be used by the devices to communicate to each other along a common network. So any packets that, like through a switch or a hub or point-to-point, they will all have local link addresses within the same network or subnet, and that's what individual devices will use to talk to each other. But these addresses cannot be used to communicate to another network. Okay, so they're not routable. They're only used within the same network segment between the devices that share that segment. They are not configured manually. They are automatically created once the interface is active, and they basically start with FE80. Okay, so if you see an address with FE80, that's a LinkLocal address. So configuration. How do we configure these on the network and how we go about it? So you go to the interface, and it's anything basically to do with IPv6 will have IPv6 as the command structure. So this command, if we're doing it in v4, would be IP address. Okay, now that we're assigning a v6, we need IPv6. So anything that you would normally use IP refers to version 4, IPv6 for v6. And that's across our show commands and things like that. That's a fairly good rule of thumb for anything to do with the two addressing schemes on these devices moving forward. So how does it work? Well, IPv6 address, and then we type in the hexadecimal notation for the interface, and then / and the prefix length. So no longer typing in the subnet mask, we just give it the prefix length, no shutdown the interface, and moving on. So on the host, exactly the same. We say it's an IPv6 address, type in the address, prefix length, and again, default gateway is all within the hexadecimal notation as well. Now, the DHCP version 6 and that mechanisms work exactly the same as what they basically do for IPv4. We just, need to get used to it. It's something a little different, but it's not that hard. And when we get into the routing protocols and that, the way we implement routing protocols and that, I think is a little bit easier under IPv6 than what we did in v4. Yeah. So local link unicast addresses are there. We can do it like we can assign it, but generally speaking, these will be automatically generated. But if you want local link addresses that are easy to remember, you can manually override these. Like if, okay, so why you would want to do this, I'm not quite sure, but you can. Okay, so if you want to manually override the one that's automatically been configured, you just do it manually, FE80, and specify that it's a link local, and that'll override the unique address that was automatically configured. As it's stating there down the bottom, you could do this so you can easily recognize the interfaces on specific routers or specific devices. But yeah. Okay. Internet Control Message Protocol. V6. So the ICMP for IPv6. Okay, so they work a little bit differently. They use router solicitation messages to discover IPv6 routers. Router advertisements will be sent by the routers to tell the hosts how they can obtain their dynamic addresses and such information that the ICMP will provide. Network prefix and prefix length, default gateways, DNSs, domain names, SLAC, stateless DHCP server addresses, and things like that. So the mechanisms work the same, but the terminology is a little different. Slack. That's what we all like to be in the afternoon, right? We all want to be slack. No? All right. Stop with the dad jokes. Yeah, I know. You're a hard crowd to work with, I tell you. All right. Devices that obtain necessary information via the GUA with the advertisements messages from the local routers, and basically they'll get given their IPv6. Well, thank you, Jacob, for laughing at the dad joke. I appreciate it. It's a bit hard to do the whole comedy routine to keep everybody awake when you're remote. It doesn't quite work the same. All right, so we can use UE64, which we'll go into in a minute, or just a random number for the 64-bit interface ID space. UE64 is very neat, and it uses that MAC address that I talked about earlier. So we'll talk about that in a few slides. All right, so take a breath, take a drink. So our advertisement message comes out and suggests that Slack to create its own IPv6 global unique address, and the router as the source Alright, so solicitation message comes out, advertisement comes back, and then part of that RA message will tell it where that DHCP server is, and then it polls the DHCP server to get all of its configuration. So it's a little different to the way DHCP works for v4. So when we're running v6, we bounce that initial request up via the router, and the routers will advise the host where to find the DHCP server. Okay. It will then push out, just like it does for IPv4, the network address, the host address, the lease, where it can find the DNS servers, the default gateways, and all that will be confirmed, and everything will be configured just like DHCP does. So again, we need to, when you're using Slack, the client needs to create the client interface ID. Now we can use UE64 or a randomly generated number. Okay, now UE, extended unique identifier, will use the MAC address, which is 48 bits, and add a little bit in the center, and we'll generate a nice little number, giving it a unique number. So the 7th bit in the client MAC address will be reversed from binary 0 to 1. So it gives it, alright, so basically we slot FFFE in the center. So if you remember, the first half identified the vendor, the second half was identified the network card. To increase that out from 48 bits to 64 bits, we add 16-bit values of FFFE into the center, and if the 7th bit's a 0, it'll change it to 1. Now, the benefit of using UE64 is you don't have to configure anything. It's just done. Because each interface requires a MAC address, so therefore it can generate the UE64 number automatically. But we can do a random generation from Vista onwards. So basically, most of the machines that we will come across in today's environment can randomly generate its own interface ID, even if it's not using the UE64 method. There is a duplicate address detection system so that the devices will not configure the same address with each other. So there's a little polling and communication, and that will go across the local links. Okay. So dynamic LLAs, so the local link addresses, and again, they can use the UE process or a random number again. But what you look out for is that FE80 leading prefix and the 64 bits. If you've set up the interfaces that you use UE 64 or randomly generate that address, doesn't matter, they'll be there. So we can create by default the UE64 interface ID. Now this is the default on the Cisco iOS routers. Okay, just makes it easier for them to have that as the default. You can change it if you want to, but by default that's what they do. Alright, so to verify, alright, so if we go back, show interface, gigabit, alright, you'll come across the MAC address, and if you do the show IPv6 interface brief, you'll see the LinkLocal being there using that MAC address with FFFE slotted in. Okay, and there's our IPv6 interface configured. So that's basically it. Multitasking is a little bit different. It uses FF00 for the multicast addresses, and yes, you'll have to remember FE80s and FF00s and the UE64 triple FE insertion into the middle. Sorry to say. Alright, so multicast addresses, FF0200, sorry, colon 1 is all nodes multicast group. Okay, so all the devices in IPv6 will join this group, and there you go. That's equivalent to, if you like, a broadcast address. And FF02 colon 2, all routers multicast group. So all the routers that are running IPv6 will join this multicast address, and if IPv6 unicast routing is enabled. Okay, so remember, multicast is a membership. So when a multicast address is sent out, each individual host will look at their destination address and go, well, I'm not a member of that multicast group, so it's not for me, or it is for me. Alright, but they'll all receive the multicast. If they're not a member of the group, they don't action it. Just like that, the broadcasts and things like that. They'll pick it up, look at it, and if it's for them, they'll action it. If it's not, they'll discard it. Alright, so the way it works is, in the big scheme of things, the 48 bits were for your identifying your ISPs, basically. And then your ISPs have this 16 bits to divvy up within their ISP or their smaller ISPs. The idea is not to go into this last interface ID, And just keep in mind that generally speaking, you'll have a /64 addressing space. So the easiest way to do subnets is just to increment the value in those last 4 digits. Okay. And they make 65,000 odd networks. So generally speaking, your service provider shouldn't really run out of addresses, should they? That's 65,000 individual ones. Now remember, if your ISP is large, has a large membership, they'll have multiple addresses. So they'll have ACAD and they'll have ACAE. They'll have a bundle of these addresses assigned to them. So allocating subnets in a block doesn't really change anything from our perspective. Each interface coming off a router needs an individual subnet. So you would take 1, 2, 3, 4, 5, 6, 7, 8, how many you need. And how do you configure it? Well, you go to each interface, type in the IPv6 address, no shed it, move to the next one, rinse and repeat for all your interfaces. So in a nutshell, IPv6 is a little different to IPv4, but the basis behind it works the same. We have a network that we can divide into subnetworks, and then we have a host portion. The number of bits that represents that combination has increased, and we represent it rather than dotted decimal notation. We are now representing it in hexadecimal notations. Okay. So we've talked about how we represent that 128 bits in groups of 4 hexadecimal values. There's no longer a broadcast, there's an Anycast. Unicast and Multicast work exactly the same. And we now have a LinkLocal address as well as a global unique address, or global unicast address as it's officially known. So we have 2. So we've got one that works anywhere in the world, and one that only works on that shared bit of cable. And we can assign the host portion, the interface ID, using UE64, which expands the MAC address. Okay. And DHCP v6 works using a route solicitation message and router advertisement message to point individual hosts into the direction of the DHCP. So it's a little different, but it still works equivalent to v4. in v4 we would send out a request for DHCP and wait for a reply from the server. In this case, we send out the request, get a reply from our router saying you are a member of this network with this prefix and your DHCP server is located here. Okay, so a little different, but basically the same. The method of automatically generating these addresses use Slack, and they can then use a combination of UE64 or just a random generated number to generate our interface ID of 64 bits in length. This is all assuming that we stick to the standard 64-bit prefix length. Once you move out of that standard 64 prefix length, all these automatic functions ceased to work in generating those automatic numbers. We have well-known multicast addresses. The two groups we talked about were the FF02:1, which is all nodes, and the FF02:2, which is router multicast groups, which the routers use to communicate to each other. All right. So that's IPv6 in a nutshell. Hopefully it wasn't too scary. And we'll stop our presentation there.